Okay, well, welcome back to Entropy Lesson 2. And we are starting on page 7 of your notes. So you will need a pen, you will need a calculator, and we will pick this up, as I said, at the top of page 7. Okay, so we're looking this time at the entropy of the system, what we call delta S system. So this is to do with the chemicals. So we have this formula, and in your exam you need to learn all the formulas. You don't get given a formula book. So the delta S system, the entropy change of the chemicals, is equal to the sum of the entropy of the products. In other words, where you end up, take away the sum of the reactants. In other words, where you started. So I'm going to work the first one out with you, and then I'm going to get you to pause the video and try the others. Okay? So first one I'm going to do is P4, white phosphorus, with oxygen reacting to form P4O10. Okay? So going through these numbers. So I've got my products, and I've got one lot of P4O10. So my delta S system is equal to 228.9. Take away where I started. Now I've got one phosphorus and 5 oxygen. So I've got 5 lots of 2O5. Okay. So this is why it's always important that we have to quote the equation that we're dealing with when we're working out our entropy change. Because if we don't, then all our numbers kind of don't work out. Now, if I get my calculator out and I plug that into my calculator and I press all the buttons correctly, I get minus 960.5. And I'm going to be careful with my units, joules per mole per Kelvin. As I said in the last video, do be very, very careful with units. Entropy is given in joules per mole, not kilojoules. Now, is your answer consistent with your understanding of entropy changes? Well, yes, it is, because it's a very large negative number. In other words, there's a massive decrease in entropy. Why? Because we're going from a solid and a gas to a solid. So, effect number 1, yes, it is consistent, because you're going from a gas, and I'm actually going from 5 moles of a gas to a solid. Therefore, entropy is decreasing because gas is more disordered than the solid. Okay, so that's the big effect. You're going from a gas to a solid, so therefore entropy must be decreasing because you're getting a lot more order in the solid. But there's a second reason, and it's important to quote both reasons. So my second reason is to do with simply just the numbers of reactants, the number of products. So I'm going from 6 moles of reactants to 1 mole of product. And therefore, entropy again must be decreasing because I've got less ways I can arrange one thing than I can arrange 6. Okay? So, if you pause the video at that point, then you can have a go at the one at the bottom of the page with hydrogen and chlorine going to HCl. Okay, so we're going to look at this second question now. So I've got hydrogen and chlorine gas reacting to form hydrogen chloride. So again, my delta S system is equal to where I end up. In this case, I've got 2 HCl, so it's 286.8. Take away where I started, which is 130.6 and 165.0. So I'm going to take those 2 away. Now, I should get an answer, if I've plugged it in correctly, of plus 78 joules per mole per Kelvin. Now, this is again consistent with what we understand from entropy changes. It's a little bit difficult, and it's quite a small positive number. And the reason for that is you're going from 2 moles of gas to 2 moles of gas. So that's not changing the entropy. The only difference between the gases is that HCl is a slightly more complex molecule. So there's slightly more microstates or ways of arranging the HCl than there is the hydrogen and the chlorine. So there's a small increase in entropy. But it's actually very difficult to actually judge from that equation whether it's going to be slightly positive or slightly negative. Much easier in the first example. Okay? So what I'd like you to do now is we're going to turn over to the top of the next page. So we've got a whole load here for you to try. There is one little correction we need to make. Somehow carbon got put with the wrong number. So can you just cross through carbon there, and it actually is 5.7. Okay, so as I said, what I'd like you to do now is pause the video and have a go at the questions on that page. Okay, so welcome back. So we should get these as our answers, and I'm just going to sort of run through them and also explain why they make sense in terms of the entropy. So the first one should be plus 446. Yes, this makes sense because you're going from a solid to a gas, and you're going from 1 mole to 3 moles, so that makes sense. The next one is plus 125.6. So again, does it make sense? Well, yes it does, because you're going from 2 moles of a liquid to 2 moles of liquid and 1 mole of a gas. So we're producing a gas, which is higher entropy, and we're going from 2 moles of reactants to 3 moles of product. Next one, number 3, is negative. Again, this is what we'd expect, because you're going from 3 moles of gas down to 2 moles of gas. So you're expecting there to be a negative change. You're expecting the products to be of more order than the reactant, so hence you've got the negative number there. The last one, down the page, again, you're going from a gas and a solid to 2 moles of gas, so you're doubling the number of moles of gas that you've got. So again, you're expecting an increase. So all of those indicate that the numbers we've calculated, the delta S system, is consistent with the equation. However, a positive delta S system on its own cannot indicate whether or not the reaction will occur spontaneously. So all of these reactions actually can, under certain conditions, be spontaneous. This reaction, I can get it to work, and I'll explain how I can get it to work later on. But a positive delta S system does not necessarily indicate that a reaction will be spontaneous. What we haven't considered is we haven't considered what is happening to the entropy of the surroundings. If you remember, we have the system, which is the chemicals, and the surroundings, which is everything else. All we've looked at so far is the system. We need to look at both the system and the surroundings to determine whether or not a reaction is feasible. And in the next video, we're going to look at entropy of the surroundings.